Triple integrals are really important because they involve integrations over space. The laws of physics are usually set over spatial regions, so knowing how to integrate over regions of space is important. But they can be a great big pain to deal with, as we saw in the last example. Very often, a change of coordinates is really useful in order to exploit the symmetry of whatever problem is to hand. A really important one is spherical symmetry. So in 3 dimensions, if a system has a planar symmetry, Cartesian coordinates are often useful. Sometimes cylindrical symmetry will be the order of the day if you're dealing with a current in a wire, for example. But often spherical symmetry, if you're dealing with a planet or something like that, will be really useful. And for that we use spherical polar coordinates. So if we have our standard Cartesian system, x, y, and z, and some point in it, we can describe this point using x, y, and z coordinates, but we can also describe it in another way. If we draw a line from the origin to the coordinate point to the point of interest, and then drop down the vertical line till I hit the xy plane, form another line to the origin, then I can label this point in space by taking the radial distance to it, the angle made with the x-axis in the xy plane, and the angle to the z-coordinate. So the angle made with the x-axis in the xy plane is phi, and the angle up to the z-axis is theta. So working out what the x, y, and z coordinates are, z is easy to see is z cos theta. The others are a little bit harder, but they both have a sine theta which projects the length into the xy plane. R sine theta is the length along here, and then times cos or sine phi, depending on whether we're on the x direction. And the way these coordinates are defined are the ranges are such that r is between 0 and infinity, theta is defined between 0 to pi, so we go from the positive to the negative z-axis, and phi goes between 0 and 2 pi as we move around the z-axis in the xy plane. Now, the key point about using these coordinates is that if we have a function which is spherically symmetric, then it just depends on the radius from the origin r. The function, given in terms of x, y, and z, can then be turned into a function which just depends on r and not theta and phi. And this makes spherical stuff easy. But how do we calculate the volume element? Well, it turns out we need, in order to do integrals, we need the volume element dv, which we know in Cartesians is just dx, dy, dz, lengths of a cube. For spherical polars, this turns out to be r squared sine theta dr, d theta, d phi. And this gives the infinitesimal volume associated with a small volume which lies along constant coordinate lines r, theta, and phi. So for example, let's say we have a planet and we know its density function. Now a planet will be, to a good approximation, spherical, and so its density function will just depend on r. Let's say its density is some constant with an exponential fall off from the center. So at the central density, it's equal to a, and then it falls off out to some radius r. So let's find its mass if its radius is r. So let's write it down. It's a triple integral over a volume of the density times the volume element. Now, in Cartesian coordinates, this would be a fairly horrible problem to try and work out. In spherical polars, it's relatively easy. So I write this down as a triple integral, and let's put on the limits. So the r is the internal one, so theta goes from 0 to pi, and phi goes from 0 to 2 pi. Now, how do we go about this integral? Well, the first thing to note is that the integrand is independent of phi. So that means we do the phi integral first. Now, the phi integral is just like integrating a constant between 0 and 2 pi, and so therefore, that just gives us a factor of 2 pi. There's different ways we can go about thinking about doing this. Do the r integral first and then the theta one, or we could do the theta one first, so swap the integration symbols around and then do the theta one first. Or in fact, let's just try a little, or in fact, one can actually separate these out. Because the integrand is separable in theta and r, we can actually write this as follows. We can write it as the product of two integrals. And that's only true because the limits don't depend on any of the variables, and the integrand is a separable function. It can be written as a function of theta times a function of r. And so now let's do the theta integral, and that just gives me a factor of 2. So we have 4 pi. And this is a whole faff to integrate by parts, but it's not very complicated. And then this becomes a slightly untidy looking function of alpha and r and a. Now, a key point to take away from this is that in general for a spherically symmetric system, where I'm integrating over some region V, If the system is spherical and the volume is spherical, then we have that this is just equal to 4 pi times the integral from 0 to r of r squared f of r dr. So it reduces to a one-dimensional integral quite quickly.